object. Here's the image. So, the image is inverted. Well, it's a real image. It's a real image. It's inverted. It's upside down, and it's magnified. Okay? It's magnified. This size is larger than that size. Okay? All right, number 2. Okay, an object is, number 2, an object is placed 3 centimeters from a concave mirror whose radius is 10 centimeters. Okay, that means it's inside the, so the radius is 10. Okay, and again, as the optic axis, I'm going to draw the mirror pretty much just as a thin mirror, pretty much just as a straight line. Okay, and this is my concave mirror. That's my concave mirror. Whoops. And here's the radius. The focal point is halfway, and the image is 3 centimeters on the inside. Okay. Excuse me. So here's the object, not the image. Here's the object, and in this case we're on the inside of the focal point. That's going to make a big difference. Okay. So ray number 1, parallel in and through the focal point. So it comes parallel in, and it would come out through the focal point. Okay, there's ray number 1. Parallel in, out through the focal point. Number 2. Okay, through the focal point and then parallel out. Okay, so we go through the focal point to the point, to the top of the object, and that would be like that, and parallel out. So it's going to hit there and come out parallel. Whoops. So there's ray number 2. Okay, through the focal point to the tip of the object and parallel out. Number 3, through the radius. Here's the radius. So we take this through the point, through the radius, and it comes right back. So here's number 3. Now notice that these 3 rays are actually diverging. These rays do not cross. So where do they cross? They cross in virtual space. They cross. So what we do is we take these rays and then we extend them back behind the mirror. And they join, the virtual rays join right here. Okay, so if here's the object and you're looking at it, all the rays converge back as if they're back behind the mirror, the concave mirror. So the image, this is the image. The image is a virtual image. Notice it's upright and it's magnified. Okay, virtual, upright, and magnified. Okay? All right. One more of these mirror problems. This will be number 3. Okay, this is, in this case, we have a convex mirror. The radius is 6 centimeters, and the object is 5 centimeters away. So the radius is 6, we're 5. Okay. This is number 3. Okay. Always use a straight edge. There's your optic axis. Okay. Again, we're going to make the concave mirror just like a straight line. Excuse me, it's a convex. It's a convex mirror, so it's bending this way. And I'm going to do this just to remind myself that it is a convex mirror. Okay. And 6, which we're going to double just for diagram purposes. There's the radius, and there's the focal point, and we're 5. Let's see, there's 5. Okay. So the object's right there. So here's the object, here's the focal point, and here's the radius. Okay. Again, same thing. First ray is parallel in, and then it goes through the focus. I'm going to make this one a little bit taller. No, I better not. I'll keep it right there. Okay, there's ray number 1. It's parallel in, and it goes through the focus. There's number 1. All right. No, that's not right. I did that like it was concave. Sorry. In concave, you know what? I drew it on the wrong side. Sorry. It's on, goodness. The focal, the mirror curves this way, so the radius is over here. The radius is on this side. My apologies. I'm not thinking. Here's the focal point, and here's the radius. It curves this way, so the radius is on the right side, the focal point's on the right side, but the object's on the left side. Okay, so parallel in, but it's going to act like it's coming through the focal point coming out. Okay, so notice that's a virtual ray through the focal point, but then it bends out. There is ray number 1. I apologize. Okay. Ray number 2 is through the focal point and then parallel out. Excuse me, I need to write something down here. Okay. Through the focal point and then parallel out. Okay, now in order to do this, we have to imagine it's going to the focal point, but it can't really get there. Okay, so we start from here, and here it's a virtual ray to the focal point, but then it's coming parallel out at where it meets the mirror. Okay, so here's the parallel out. The convex mirror is definitely a harder problem to do, because the focal point and radius is on the opposite side, so you have to connect where the line would be or would be going into the focal point and radius on the opposite side. So the convex mirror is definitely a harder optic piece to draw than the concave. Okay, number 3, so but there's number 2. It goes through the focal point, or it would go to the focal point if it could, but then it comes parallel out. Okay? Number 3, it's through the radius. Through the radius. Now, through the radius, that's way over here. So we draw it as if it would get to the radius, but then it comes right back out along the same line. So we line up this with the radius, and then this is a dotted line. It can't get to the radius, but it acts as if it does get to the radius, and then it's parallel, then it comes right back out on itself. So here's number 3. It goes in this way, and then right back out, and it acts as if it would come here. Well, we didn't really draw this very well. Well, maybe no, actually I think I did. Because where we have this, let me see here. If we had, essentially these are trying to meet right in here. Now one kind of misses it. I'm not quite sure why we're off on that one. But essentially where these, notice that the rays on the left-hand side are diverging. So they have to converge where the virtual rays are coming on the right-hand side of the lens, or the mirror, and essentially they're somehow this one's off. Not quite sure why that is, but there's the image. And what is it? It is a virtual image. It's a virtual image. It is upright, and it's reduced. Okay? This is definitely a harder one to draw. Okay, that's number 3. All right, number 4. Let me get my calculator here. Okay, number 4. Light is traveling in air, and it's incident on a block of ice at an angle of 25 degrees. So here's a block of ice, and this angle is 25 degrees. Coming in 25 from the vertical or the normal. That's what we mean. There's the angle. We'll call it theta 1. What is the angle of refraction? So the question is, it's going to refract and find theta 2. So from Snell's law, well, the index of refraction of air is 1. Index of refraction of the ice is given as 1.31. Okay, so from Snell's law, this is Snell's law. We want to solve for theta 2 or sine of theta 2. So let's first do the sine of theta 2 is equal to n1 sine of theta 1 divided by n2. So this would be index of refraction of 1. of N1 is 1, so it would be the sine of 25 degrees divided by 1.31, which is 25 sine divided by 1.31, or 0.3226. The angle now is simply the inverse sine, or the arc sine, of 0.3226, and I do the arc sine, or inverse sine, and I get that that angle is 18.8 degrees. So that's what this angle is here, 18.8 degrees. Or I should really round this off to 19 degrees. Two significant figures here because I have two significant figures here. Okay, number 5. Well, number 5 is a good question, and it deals with total internal reflection, what we call total internal reflection. Okay. Okay, number 5. When light travels from a substance and encounters another substance with a lower index of refraction, there are some angles of incidence for which refraction is not possible. For those angles, the light is totally reflected back into the substance. This phenomenon is called total internal reflection. Okay, and let's consider this. Okay, for instance, we have a block. In this case, what we have is we have glass. This is glass, and this is air. This is number 5. And all the problems so far have been where the light is coming down from the air into the glass. This way is different. Now the light is traveling from the glass into the air. Okay, so the index of refraction of glass is 1.5. Index of refraction of air is, of course, 1. Okay, consider, it says, consider, for example, light traveling in glass and encountering air, angles of incidence ranging from some theta tr total reflection to 90 are totally reflected back into the glass. What is this angle for the situation? Okay, what we mean is this. Okay, suppose okay, here's the normal. Suppose this angle is quite steep or quite small. Suppose this angle 1 is 10 degrees. Okay, just as an example. And this, when it's going into a less dense media, it angles at this, it bends out, we know. Snell's law is that theta 1, and this, we're going to call this, it doesn't really matter which one, but we'll call this one theta 1, or N1, and we'll call this N2. Okay, so N1 sine of theta 1, this will be theta 1, equals N2 sine of theta 2. Okay, we're going to solve for theta 2. So again, sine of theta 2 equals N1 sine theta 1 divided by N2. So if we put in here, let's use a small angle here. Okay, notice what we have. We'd have sine of theta 2 equals N1 is 1.5 times sine of 10 degrees. Okay, notice N2 is 1, so N2 is equal to 1, so we're not able to write it in. It's simply divided by 1. So this is 10 degrees, take the sine of that, times 1.5 and I get 0.26047. The angle here, the angle is therefore the arc sine, inverse sine of 0.26047, which is 15 degrees. 15 degrees. Okay. So that'll be 15 degrees. But let's suppose we increase this. Let's suppose we increase it to 20 degrees. Okay. Now I'm going to increase this to 20. The sine of 20 times 1.5 is 0.513. The inverse sine of 0.513 is about 31 degrees. Okay? So for the 20 degrees here, this would be about 31 degrees. Let's increase it some more. Let's increase this to 30 degrees. Okay? You may be able to see where I'm going with this, but maybe not. Okay, this is 30 degrees now. Okay, I take the sine of 30 degrees times 1.5, and I get 0.75. And I take the arc sine of 0.75, and I get 48.5. Okay? So far, so good. Now, I'm going to increase it even more. Let's make it 40 degrees. Okay, sine of 40 degrees. So what I'm really doing here is I'm making this angle, I'm widening this out. It was here, now I'm widening it out, and so this is going to bend even more. Okay? So at 40 degrees, sine of 40 degrees, sine of 40 degrees times 1.5 is 0.964. I take the inverse sine of that, and I get 74.6 degrees. Okay, so a pretty steep angle. Now I'm going to make it 45 degrees. Okay, I'm going to increase a little bit more to 45 degrees. This is 45 degrees. And let's see what this angle is. It's going to be, I'm going to make it steeper. Okay, 45, sine of 45 times 1.5 is, 1.0607. So I do the inverse sine of 1.0607. I do that, and lo and behold, I get 0. In fact, I get an error. So I cannot take the sine of something that's, notice that this is a little bit greater than 1. Okay, well, let's think about this. What is the sine, the inverse sine of 1 exactly? Well, it's the inverse sine of 1. Do this. Take 1 into your calculator, and then do arc sine, and what do you get? You get 90 degrees. Okay, so at some point, this angle is going to be so steep, it's flat, and it's 90 degrees. Okay, what angle is this? What angle is? Well, we can solve for that. Let's work this thing backwards. If we want this to be exactly 90 degrees, if we want this angle to be exactly 90 degrees, let's solve for what this angle is by working this backwards. Okay? So, basically we want this to be 1. That's 1. And so, whatever this theta, this is theta 1 here. So we want 1.5 times sine of theta 1 to be 1. So basically the sine of theta 1 is 1 divided by 1.5. 1 divided by 1.5, which is 0.6666, and it keeps on repeating. And now I do the inverse arc sine of that theta, and I get 41.8, 8 degrees. So what does this mean? This means that when theta 1 right here is 41.8 degrees, when this angle is 41.8 degrees, theta 2 is exactly, has just reached 90 degrees. Okay? So now what happens if we make this angle now any steeper? I'm going to use blue for this. If we make this angle any steeper, like here, does this change? No. It still remains 90 degrees. Now what physically happens, and at this point, this energy here is called total internal reflection. This is a condition for what we call total internal reflection. And what physically happens is that the energy that gets refracted here becomes very less, and all the energy goes into what's reflected. Remember, now we haven't talked about the reflected ray, but there's always a ray this would be the refracted ray, and this is the reflected ray. Okay, so basically, when we have theta 1 that's equal to or greater than 41.8, all the rays become reflected back into the glass. Okay? So this is a condition called total internal reflection. And this is not really part of the chapter, but he threw this question in, and it's a very good question because it makes you think. So basically, how do you solve for this? You set this up, and then it's a condition for which the sine of the angle 2 equals 1. And then you solve for what angle makes that true for. Okay, where is this practically used? This whole idea of total internal reflection is used all the time in fiber optics. And what we mean by that is this. And well, what does that look? What does it look like? Remember, suppose I'm going to now take this and I'm going to get rid of this Snell's law math here. And this is glass and this is air, but now suppose I'm going to do this. I'm going to put another boundary right over here. So this is glass, this is air, this is glass, but this is back air again. This is like this is kind of like a fiber optic, or what we call optical fiber. It's a fiber that's made of it's a glass or plastic. These are either made of glass or plastic, and they're extruded out at high temperatures, kind of like making wire. And so what happens is, if we have a laser, say we have a laser, and we shoot the laser right in here, we have a nice clean edge. We shoot the laser in. Say we have shoot the laser in, so the angle here is a very low angle. I'm going to raise this up a little bit. The angle is quite low. Okay? That is low to here, but this angle here is very high. This angle may be, 80 degrees. Okay, it's a very high angle. All of the energy, but because we're way beyond the point of total, the minimum total internal reflected angle, all this energy has to be reflected. It has to. None of it can escape because we're beyond the point where Snell's law, we're outside the point where Snell's law allows it to escape out the fiber. And so all of the energy, in fact 100% of the energy, with the exception of some minor losses, but essentially 100% of the energy gets reflected. And so what we have, if we have a thin pipe, is the energy just bounces from side to side like this. And if you would look, if I could do another diagram of an optical fiber, the light comes in and it simply bounces and it bounces and it bounces and it bounces, and that's exactly how light travels down a fiber optic. We call it the waveguide. This is called a waveguide. A waveguide, and it happens in optics, but it also happens in radar. It happens in any electronic or electromagnetic media where you have boundaries, and all the energy just travels right down the waveguide. Okay, so this is essentially this is the whole principle. Snell's law is what makes what makes communications in optical fibers so great. All the energy is trapped inside of the fiber. Okay, and it will transmit like this for literally